So this continues on where I left off. So now I'm at the bottom of 226 and top of 227. Just going to read the value in the ADRESH, ADRESL registers is not modified for a power on reset. The ADRESH, ADRESL registers will contain unknown data after a power on reset. After the AD module has been configured as desired, the selected channel must be acquired before the conversion is started. The analog input channels must have their corresponding trice bits selected as an input. To determine acquisition time, see section 19.1, AD acquisition requirements. After this acquisition time has elapsed, the AD conversion can be started. An acquisition time can be programmed to occur between setting the go done bit and the actual start of the conversion. The following steps should be followed to perform an AD conversion. Configure the AD module, configure analog pins, voltage reference, and digital I/O ADCON 1. Select AD input channel, ADCON 0. Select AD acquisition time, ADCON 2. Select AD conversion clock, ADCON 2. Turn on AD module, ADCON 0. Configure AD interrupt if desired. Clear ADIF bit. Set ADIE bit. Set GIE bit. Number 3. Wait the required acquisition time if required. Start conversion. Set go done bit. ADCON 0 register. 5. Wait for AD conversion to complete by either polling for the go done bit to be cleared or waiting for the AD interrupt. Read AD number 6. Read AD result registers ADRESH, ADRESL. Clear bit ADIF if required. For next conversion, go to step 1 or step 2 as required. The AD conversion time per bit is defined as TAD. A minimum wait of 2 TAD is required before the next acquisition starts. AD transfer function. Digital code output. 00H up to 3FFH, so that's hexadecimal, I guess. I better not comment. Analog input voltage. 0.5 LSB up to 1023.5 LSB. Analog input model. Voltage analog input, and then it's grounded, and then it goes through RS. What's RS? Well, it's a resistor, but anyway, maybe I'll figure it out later. What does the dotted lines represent? ANX, maybe that's whatever pin is selected for analog inputs. C pin 5 picofarad. VDD, and maybe this is the diode, so this is the power source. So I don't know how these diodes work. And what's this? The threshold voltage, VT, and then leakage, plus or minus 100 nanoamps. RIC is interconnect resistance, and greater or minus, or sorry, yeah, less than or equal to 1K. Sampling switch. SS is the sample switch. RSS is sampling switch resistance. C hold equals 25 picofarad. Sample hold capacitance from DAC. VSS is VSS or ground. VDD 2 volts to 6 volts. Sampling switch kiloohms. So 1 kiloohm, 2 kiloohm, 3 kiloohm. Sampling switch. I should read the legend, maybe. Maybe I should have read that first. Legend, C-pin. Input capacitance. VT. Should I identify them on the chart? Okay, input capacitance. Here it is here, 5 picofarad. VT, threshold voltage. That's for the diodes. VT, I think. I leakage, 100 nanoamps plus or minus. Interconnect resistance, RIC. Okay. Sampling switch, C hold, sample hold capacitance from DAC. Sampling switch resistance, RSS. It's page 227. AD acquisition requirements. For the AD converter to meet its specified accuracy, the charge holding capacitor, C hold, must be allowed to fully charge to the input channel voltage level. The analog input model is shown in figure 19.3. The source impedance, RS, and the internal sampling switch, RSS, impedance directly affect the time required to charge the capacitor, C hold. The sampling switch, RSS, impedance varies over the device voltage, VDD. The source impedance affects the offset voltage at the analog input due to pin leakage current. The maximum recommended impedance for analog sources is 2.5 kiloohms. After the analog input channel is selected, changed, the channel must be sampled for at least the minimum acquisition time before starting a conversion. Note, when the conversion is started, the holding capacitor is disconnected from the input pin. I'll move up here. To calculate the minimum acquisition time, equation 19.1, so that's here, may be used. This equation assumes that the 1 divided by 2 LSB error is used, 1024 steps for the AD. The 1 over 2 LSB error is the maximum error allowed for the AD to meet its specified resolution. Example 19.3 shows the calculation of the minimum required acquisition time. Talk Q. This calculation is based on the following application system assumptions. C hold, 25 picofarad, RS, 2.5 kilo ohm. Conversion error 1/2. Conversion error is less than or equal to 1/2 LSB. VDD equals 5 volts to RSS equals 2 kilo ohm. Temperature is 85 degrees Celsius, system max. I think I read this, but I'll read it again. Note: when the conversion is started, the holding capacitor is disconnected from the input pin. Equation 19.1. Acquisition time. Torque Q. Amplifier setting time plus holding capacitor charging time plus temperature coefficient. Temp plus Tc plus Tcoff. Equation 19.2. AD minimum charging time. Vhold equals Vref minus Vref divided by 2048 multiplied by 1 to the log of all this stuff, which I suppose has been defined. Or Tc Hold. Should I read all this? Well, I'll read the headings. Calculating the minimum required acquisition time. Well, yeah, I won't read it. I suppose if I need to calculate that kind of information, which I might need to, I can come back. Alright, scrolling down. 19.2. Selecting and configuring acquisition time. The AD-Con2 register allows the user to select an acquisition time that occurs each time the go done bit is set. It also gives users the option to use an automatically determined acquisition time. Acquisition time may be set with the ACQ-TQ T2 to T0 bits, ADCON 5 to 3, which provides a range of 2 to 20 TAD. When the go done bit is set, the AD module continues to sample the input for the selected acquisition time, then automatically begins a conversion. Since the acquisition time is programmed, there may be no need to wait for an acquisition time between selecting a channel and setting the go done bit. Manual acquisition is selected when ACQ-T2 ACQ-T0 equals 000. When the go done bit is set, sampling is stopped and a conversion begins. The user is responsible for ensuring the required acquisition time has passed between selecting the desired input channel and setting the go done bit. This option is also the default reset state of the ACQ-T2 T0 bits and is compatible with devices that do not offer programmable acquisition times. In either case, when the conversion is completed, the go done bit is cleared, the ADIF flag is set, and the AD begins sampling the currently selected channel again. If an acquisition time is programmed, there is nothing to indicate if the acquisition time has ended or if the conversion has begun. So I cut off the top there. So that was selecting and configuring acquisition time. Selecting the AD conversion clock. The AD conversion time per bit is defined as TAD. The AD conversion requires 11 TAD per 10-bit conversion. The source of the analog to digital conversion clock is software selectable. There are 7 possible options for TAD, from T-TOSC to 64-TOSC. Internal RC oscillator. For correct AD conversions, the AD conversion clock TAD must be as short as possible, but greater than the minimum TAD. See parameter 130 for more information. Table 19.1 shows the resultant TAD times derived from the device operating frequencies and the AD clock source selected. Okay, that's where I finished. Scrolling down right now, we're on page 229, table 19.1, TAD versus device operating frequencies. Here's the operation. I guess that's the oscillator configuration. I'm tired here. ADCS2, ADCS0. I scrolled back up the page just to point out that this ADCS2 and ADCS0 appears in the ADCON2 register. And it shows the different configurations, zeros and ones. Maximum device frequency. I'll skip reading these notes. Alright, this will be the last page of this video on page 2. This one's 230. Operation in power managed modes. 19.4. The selection of the automatic acquisition time and AD conversion clock is determined in part by the clock source and frequency while in a power managed mode. If the AD is expected to operate while the device is in a power managed mode, the ACQT2, ACQT0, and ADCS2 to 0 bits in the ADCON2 should be updated in accordance with the clock source to be used in that mode. After entering the mode, an AD acquisition or conversion may be started. Once started, the device should continue to be clocked by the same clock source until the conversion has been completed. If desired, the device may be placed into the corresponding idle modes during the conversion. If the device clock frequency is less than 1 MHz, the ADRC clock source should be selected. Operation in the sleep mode requires the AD/FRC clock to be selected. If bits ACQT2 to T0 are set to 000 and a conversion is started, the conversion will be delayed one instruction cycle to allow execution of the sleep instruction and entry to sleep mode. The IDLEN bit OSCCON (7) must have been cleared prior to starting the conversion. Configuring analog port pins. 19.5. The ADCON1 Trice A, Trice B, and Trice E registers all configure the AD port pins. The port pins needed as analog inputs must have their corresponding Trice bits set input. If the Trice bit is cleared output, the digital output VOH or VOL will be converted. The AD operation is independent of the state of the CHS3, CHS0 bits, and the Trice bits. CHS3 to CHS0 is contained in the ADCON0 register. Note 1. When reading the port register, all pins configured as analog input channels will read as cleared, a low level. Pins configured as digital inputs will convert as analog inputs. Analog levels on a digitally configured input will be accurately converted. Number 2. Analog levels on any pin defined as a digital input may cause the digital input buffer to consume current out of the device's specification limits. Pin 3. The PBADEN bit in configuration register 3H configures port B pins to reset as analog or digital pins by controlling how the PCFG30 bits in ADCON1 are reset.